this video I'll be taking some of the previous year questions from the topic laminar and turbulent flow. So the first question is, consider laminar flow of water over a flat plate of length 1 meter. A flat plate of length 1 meter is given if the boundary layer thickness at a distance of 0.25 meters from the leading edge of the plate is 8 mm. At a distance of 0.25 meters from the leading edge of the plate is 8 mm. This is the boundary layer thickness. The boundary layer thickness in mm, be careful of the units, at a distance of 0.75 meter is. Okay, for laminar flow over a flat plate, okay, we know that this boundary layer thickness is directly proportional to x raised to the power 1 by 2, and x is the distance from the leading edge. Okay, we know this relation, distance from the leading edge. So this becomes a pretty simple question. That implies delta 1 by delta 2 is equal to root of x1 by x2. Okay, you have all the values. This is 0.25, 0.75 meters, and del 1 is, this is 0.008 meter. Okay, so solve this, you'll get del 2, that is the boundary layer thickness, okay, at a distance of 0.75 meters from the leading edge, that you will get as 13.8564 meters. Sorry, mm. This is mm. Okay, so this relation is quite important. This relation is quite important. Okay, next question. Consider the turbulent flow of a fluid through a circular pipe of diameter d. Turbulent flow is given. Identify the correct pair of statements. The fluid is well mixed, the fluid is unmixed, Reynolds number is less than 2300, Reynolds number is greater than 2300. So for turbulent flow, what are the characteristics? That the fluid is well mixed, yes, correct. Viscosity is due to molecular momentum transfer. Okay, velocity distribution is logarithmic in turbulent flow. The flow is highly disordered due to random mixing, and in turbulent flow there is a high velocity and low viscosity, and the Reynolds number is greater than 2300. So the Reynolds number is greater than 2300. So the options that are correct, okay, identify the correct pair of statements. Those are 1 and 4, that is option D. Next question. The Blasius equation related to boundary layer theory is, okay, the Blasius equation is d cube f by dn cube plus f by 2 d square f by dn square. This is the Blasius equation. Okay, so from this equation what we can see, it is a third order equation. Okay, it is a third order ordinary differential equation, and it is non-linear because the dependent variable has been multiplied with its derivative, so that makes it non-linear. So the answer is third order non-linear ordinary differential equation. The option will be, I guess, third order non-linear ordinary differential equation, that is D. Okay, next question. The air having a density and kinematic viscosity is given. This is nu, 2 into 10 to the minus 5 meters square per second, with a velocity of 2 meter per second, flows over the top surface of a flat plate. Flat plate is given, length 2.5 meters. If the average value of friction coefficient is okay, the relation that you learn is also given, so that makes it again a simple question. You have been asked the value of the total drag force in Newton per unit width. Okay, per unit width of the plate is, so CF, that is average value of friction coefficient, is equal to drag force upon half rho a v square. This we know the relation, okay, and it is equal to 1.328 upon under root Reynolds number. So here for total drag force, x will be equal to L, so that implies we have to find Reynolds number at x is equal to L. Okay, so Reynolds number is Vd by nu. Great. We know V, yes, it is 2 meter per second. D is the characteristic length here, which is 2.5 meters. Okay, and nu is also given, that is 2 into 10 to the power minus 5 meter square per second. Be aware of the units. So Reynolds number is 2.5 into 10 to the power 5. Okay, so that implies if we put the Reynolds number here, this Reynolds number here, we get the value of friction coefficient. Okay, so drag force will be half rho av square into cf. Okay, so solve this. Half rho is what, 1.2 kilogram per meter cube. I'm again saying be careful of the units. Area, this is the length, this is the width, so they have asked us to find the total drag force per unit width. Okay, so this, let this be w. Okay, the length is 2.5, area, that is w, I mean 2.5 into w is the area, v square, 2 square into cf, 1.328 upon root of Reynolds number, that is 2.5 to 10 to the power 5. Okay, this we have found out. So take this w below fd. Okay, so this becomes fd, I mean drag force per unit width. Okay, solve this. The answer will be 0.0159 newtons. Okay, so let's move on to the next question. For a fully developed laminar flow, okay, fully developed laminar flow is given of water, dynamic viscosity mu is 0.001 Pascal second. It's given through a pipe of radius 5 centimeters. So be aware that here radius is given. Okay, generally we are given with diameter, here radius is given. Okay, so be careful. The axial pressure gradient is minus 10 Pascal per meter. Okay, the magnitude of axial velocity at a radial location of 0.2 centimeter. Great. So just a rough diagram. Okay, center line, capital R, which is 5 centimeter. We have to find the axial velocity at this R, this small r, let it be small r, and the distance where we have to find this velocity is 0.2 centimeter. Okay, so mu is 0.001 Pascal second. Okay, capital R is 5 centimeters, that is 0.05 meter. Okay, del P by del X, pressure gradient, which is minus 10 Pascal per meter. Okay, so axial velocity at a radial location of 0.2 centimeter, that is change it in meter, 0.002 meter, is found out by relation. We know this relation, u is equal to minus 1 by 4 mu del P by del X, capital R square minus R square. Okay, this is the radius of the pipe and this is that radial location where you have to find the velocity. Okay, so put all the values, you have all the values. 1 upon, I mean this is 0.001 into 10 to 0.05 whole square minus 0.002 square. So this will give you u, which will be equal to 6.24 meter per second. Again a pretty simple question based directly on the formula. Okay, so before going on to the next question, this relation is, I'll tell you, this relation is quite important. Many questions have been asked in past on this relation and that relation, that the boundary layer thickness is directly proportional to x raised to power 1 by 2, where x is the distance from the leading edge. This relation is also very important. Okay, many questions have been asked on this relation also. this relation was used in the first question of the video. This is also important. So next question. Co-wet flow is characterized by, okay, uh, co-wet flow, a steady incompressible laminar flow takes place between one fixed plate and a moving plate with a constant velocity. Okay, so whatever be the options, we can match the answer. That is, I guess this is option D. So co-wet flow is characterized by steady incompressible laminar flow between one fixed plate and the other moving plate with a constant velocity. Okay, thank you.